Welcome to Control 4 Driver Development Essentials. My name is Peter Casenza. The purpose of this training module is to expand even further upon our two previous videos. In those videos, we examined driver code and saw how data moving between the Control 4 system and a controlled device is managed through Lua tables and sent and received through DriverWorks APIs. We also looked at how data must be parsed into a manageable format for both the devices and the Control 4 operating system. This video will delve deeper into the data parsing aspect of driver development. We will begin by discussing the data type categories most commonly found in device protocols. Then, we'll examine several Lua libraries that deal specifically with data parsing. We'll also show you how to set up a free Lua development environment to experiment with the libraries. We'll then use that development environment to review examples of the most common Lua functions and explain how they are used in Control 4 drivers. Additionally, the content of this training video is supported with a supplemental document titled 401 Module 7 Lua Parsing Examples. This document provides further details on the examples we'll review, as well as additional Lua exercises. Before we begin discussing Lua, it will be worthwhile to review the two most common data type categories you will encounter as a driver developer. The first is ASCII. Previously, we defined ASCII as a character-based encoding format that is based on the alphabet. It encodes 128 specified characters into 7-bit binary integers. The characters include the numbers 0 through 9, the letters A through Z, some punctuation symbols, control codes, and a blank space. In this video, we will be using an ASCII data string example of load space 23 space 80 /n. This is a data string that comes from a light dimmer. As we discussed in previous training modules, this string would come from the device to the Control 4 system through a DriverWorks driver API, such as received from network or received from serial. The second type of data we will discuss is hexadecimal. We have defined this string type as a format using 16 symbols to represent values 0 through 9 and upper and lower cases of A, B, C, D, E, F to represent values 10 through 15. In this video, we will be using a hexadecimal data string example of 01, 03, 014B, 50. This example also reflects a data string sent from a light device, such as a dimmer, to the Control 4 system. Again, it would be received by the system through the appropriate DriverWorks API. We'll be demonstrating Lua functions in a development environment that uses Notepad++ and a Lua library. Both of these items are free, and when used in conjunction with each other, they provide a great modeling environment for you to exercise Lua functions. Let's take a minute and review how you can set up this environment for yourself. You will need to download the latest version of Notepad++ from the web. In our example, we'll take the option to use the installer. Simply download and run the executable file. You can accept all of the defaults during installation. From within Notepad++, you will need to install the npp exec plugin. Do this by clicking on the Plugins option from the toolbar. Click on Plugin Manager and select Show Plugin Manager. Find the npp exec plugin from the list and install it. Now go back into Plugins and open up nppexec. You'll want to select the following: Show Console Dialog, Console Commands History, No Internal Messages, and finally, Follow $current directory. Once they are selected, go back into Plugins and open nppexec again. This time, select Execute option. You'll want to modify this screen to reflect the following and click Save. Your Notepad++ environment is now ready to use. This is the same environment we will be using throughout this training module. Lua is comprised of numerous libraries. The first library we'll examine is the string library. The string library is comprised of functions that are designed to operate on data strings. And while they vary in complexity and purpose, many utilize data patterns. Data patterns are very powerful elements that, when fully understood, enable you to develop better and more efficient string parsing. What is useful to us as driver developers is the string library's function ability to capture parts of the data string that match parts of the pattern for further use. Lua defines the individual elements that can be combined to create a pattern character class. A pattern character class can also be considered an expression. For example, here is the list of the pattern character classes supported by Lua. As you can see, each of the character classes are made up of elements. In addition to this, there are other elements defined by Lua that can be used in pattern matching. Delimiters are included in the library. These are elements such as a space or a parentheses. Modifiers are characters that can make patterns more useful with matching one or more characters or dealing with repetitions. Literals can also be used in the case where an element in a pattern is used to capture the literal version of a character within a data string. Lua also provides a list of special characters that have special meaning when used in a pattern. These include the following characters. Each of the string library functions rely on these elements that are defined by Lua. When the correctly formatted parameters are passed through a string library function, they will return parse data in a desired format. In Lua, these elements are specifically named character classes. Some examples of character classes include dot, which when passed will return any character. The use of %a will return any letter, and %u will return any uppercase letter. In addition to pattern character classes, modifiers can be appended to the pattern character class to further increase pattern matching and data capturing. For example, the modifier plus matches one or more characters of the original pattern character class. It will always get the longest sequence that matches the pattern. For example, the pattern %a plus means one or more letters, or even a word. The combination of pattern character classes and modifiers that can be used within the functions is what makes the string library so powerful. We will use several pattern character classes and modifiers in this training module. However, the complete list of pattern character classes and modifiers is lengthy and warrants full review outside of this video. We recommend the following Lua resource for this purpose: www.lua.org. Now that you have some background on the Lua string library, let's take a look at one of its more popular functions used in Control4 drivers. It is named string.match. String.match is useful in that it can be configured to capture a wide variety of data character patterns. It requires the use of several elements that, when properly assembled, can return data string components. One or more pattern configurations can be passed through a single instance of string.match. This function can be used to review and parse the content of both ASCII or hexadecimal strings. By default, it begins to examine a data string at position 1. However, it can be configured to start at any position. All of the pattern samples in our string.match examples use defined Lua pattern character classes and modifiers. The prototype of string.match looks like this. As we mentioned, string.match requires several parameters. The parameters used by the function include S, which represents the actual source string that will be parsed by the function, P, which is the defined Lua pattern elements, such as character class and modifiers, that the function will use. Finally, the optional parameter I can be used to start string.match's data string parsing process in any position within the string where I represents a number correlating to the position in the string where the parsing will begin. Let's take a look at a few examples of using string.match in a light driver to see how it works. Let's assume that we've received an ASCII string from a light device, such as a dimmer, that looks like this. We know from reading our protocol documentation that data strings coming from this particular light device begin with a notification followed by a space, then a load number followed by a space, and finally the current load level. We also know that each command ends with \n. Based on this, we can easily see that the load notification has been sent for light 23 and its current light level is 80. As a driver developer, you can use string.match to parse through data strings of various lengths or numerous data strings to capture the portion of data that we're most interested in and place them into a manageable format for the Control4 system. To further understand how this is accomplished, we'll create a function named test1. It looks like this. Line 2 of the code uses the print function. You'll see this used throughout the examples in this training module. The print function allows us to see the results of our code in the output window. Let's examine the code and see how this example of string.match works. Line 3 of the code defines a local variable named message. This variable holds the string that will be parsed. In line 4, we've created another local variable named pattern. This variable holds the Lua pattern that will be used to capture the desired data string components within the string. This capture pattern is the instruction set that string.match will use to parse the contents of the message variable. Let's take a close look at the contents of this variable, as understanding its components will help in understanding how pattern character classes and modifiers are used to parse our example data string. So how exactly do we search for load? We accomplish that by using our first example of a character class and a modifier. The first pattern we will search for is .plus. It uses the character class dot. Dot will search for and return any character. Immediately following the dot, we added a modifier, the plus symbol. Appending the plus modifier to a character class requires that there be at least one character present in this portion of the data string for it to be valid. Notice that our pattern is surrounded by parentheses and followed by a space. This will capture our notification, which in this example is the string value load. Note that it is followed by a space as seen in our message format. This is an example of a space being used as a delimiter. The next pattern we will search for is %d+. The pattern character class %d will search for and return any digit. Once again, we're using the plus modifier that will require that at least one digit be present for a valid return value. This will capture our load num value, or 23. The next pattern we'll use in string.match is once again %d+. It will capture our level value, or 80, in the same manner as 23. Note the use of parentheses that surround our pattern, as well as the use of spaces as delimiters before and after the values. These are important components as the string we are parsing requires them. Finally, the string ends with the \n, which indicates the end of a message. We know this as it is defined in our protocol documentation. Up to this point, we've been able to construct a group of Lua pattern elements using character classes and modifiers to parse our example data string. If you look at the code, you'll notice that we added an open and close parentheses immediately following the string end symbol, \n. This is a Lua convention often used in Control4 drivers. It is useful as it will return a value that reflects the numerical position of its location within the string. For example, if you count the positions of the string, beginning with the L in load, and ending with the position immediately after the \n, you will count 11 positions. Our function should return a value of 12. By having this value returned by string.match, we can verify not only the correct string length, but the correct string position of the open and closed parentheses. Now that we've broken down our local variable pattern, let's look at where string.match is actually called. It uses the two local variables that we defined above it, message and pattern. These are separated by a comma. Next, our print function will print the result of each of the parameters that we have passed through string.match. If we run the test1 function above, we will see the following output. Let's look at another string.match example using the same late load data string. However, this time our string has been formed differently. It now looks like this: LD 23 80 \n. Note the lack of spaces or delimiters in this syntax. This will allow us to use some elements that can take advantage of this message's fixed length. Using string.match and its Lua defined pattern elements, we can create a function to parse this string. It looks like this. Let's break down the string.match elements we've used. Once again, our string.match function begins with the first parameter, which uses the local variable message. It is followed by our pattern variable. Let's break down the pattern variable to understand how some new pattern character classes are used to parse our data string. The first pattern element we'll use is the dot character class. The use of a single dot will look for any character. Two dots used together within the parentheses will return the first two characters of the string, or LD. Note that we are not using spaces to separate our patterns in this example. If we look at the string we're trying to parse, we can see that it contains no spaces. You can see that we use the same pattern elements for the next two patterns. This will return our load num and level values, or 23 and 80. Once again, we see the string termination syntax, or front/n. We'll use the open and close parentheses to return a position value for us in this example as well. The parentheses are placed at position 8 in our example. When we run our function, the output looks like this. Let's look at one more string.match example. You've probably noticed that our string.match syntax can rely heavily on the use of parentheses. But what if the string we need to parse has several instances of parentheses within it? Consider a data string coming from our dimmer that looks like this: load, space, paren 23 paren, space, angle bracket, 80, angle bracket, \n. The Lua string library uses special or magic characters. This example uses the special character %, which works as an escape. In this example, we need to use the special character left parentheses, but the left parentheses is a magic character and therefore needs to be escaped. The escape character is the % character. So, by putting in a % left parentheses, we are using the literal character rather than its special meaning. Using this, we can create a function to parse this string that looks like this. Let's go right to the pattern variable and break it down. The first pattern elements we'll pass are the .character class and the plus modifier. As we have stated, the use of a dot will look for any character, and the addition of the plus modifier requires that there be at least one character present for a valid return. This pattern will return load. Next, we need to handle the open parentheses before the 23 value in the data string we received. We do this by passing the special character % followed by the left parentheses. Now that the open parentheses is handled, we can do a pattern match search of %d+. This will find any digit and require there be at least one digit present. We can't forget about the parentheses after the 23 value. We handle it with %right parentheses. It is important to understand the % left parentheses and %right parentheses in this example. It allows for the use of the parentheses in a literal manner in our pattern while not returning any data. Our next set of elements is an interesting variation to the ones used for 23. Here we see the use of angle brackets to delimit our value of 80. Here we do not use the % escape character since angle brackets are not special characters. The %d+ pattern will find any digit and require that there be at least one digit present. It will capture our value of 80. Finally, we'll use our position pattern of open and close parentheses. It should return a value of 14. When we run our function, the output looks like this. It's important to keep in mind that ASCII isn't the only data type that you'll encounter when writing a device driver. The hexadecimal data format is just as important and warrants close examination. In order to illustrate an example of how to parse a hexadecimal string, we'll need to take a close look at the protocol we're dealing with. We're going to use the same type of example as we did with string.match. We'll receive a load-related data string from a dimmer. If we look at the protocol for this device, we can ascertain a few important items. The first is that the load command contains a total of 5 bytes. If we broke the command down and look at it from a byte-by-byte perspective, the command looks like this. The first byte is the command, and it is 1 byte in length. The second byte is reserved for a data length value. It too is 1 byte. This is the number of bytes found in the remainder of the string, which is 3 bytes in our example. The remaining 3 bytes left in the string are reserved for the message portion of the hex string. The first and second bytes are the load number. The last byte is the load level. Our hexadecimal command looks like this. The load command is 01. The 03 is the data length of 3 bytes, which is comprised of the load number and the load level. The 014B is the hexadecimal value for 331. This is the number assigned to our device. Finally, 50 is the hexadecimal value for 80, which is the level of our dimmer. Now that we know what our data string looks like, let's review some Lua functions that can assist us in parsing the string into manageable pieces. In this example, we're using 3 Lua functions: string.unpack, string.sub, and string.pack. We'll also be demonstrating the use of the Lua window in Composer Pro. It represents another viable option for modeling your Lua commands. To set up Composer Pro to work as a Lua development environment, simply run Composer Pro in virtual mode and load any DriverWorks driver. You can access the Lua window under the Properties tab for the driver. In this example, you can see that we've once again created local variables for the load number data and the load level. You'll also notice that we're using hexdump. Hexdump will display the hex string received in the data message in our output window. If you look at this line of the code, you'll see that we are using the string.unpack Lua function. String.unpack is a function that will take the contents of our hexadecimal data message and parse it into its elements. These elements are the ones we discussed earlier: the command, data length, and data string comprised of the load number and the load value. We are also using the Lua function string.sub. String.sub will return a substring of our original hexadecimal string. The use of string.unpack and string.sub accomplishes 2 tasks. String.unpack parses the hexadecimal string, and string.sub pulls out a portion of that string. You'll notice the use of the parameter bb in string.unpack. Each b represents 1 byte in our data message, working from left to right. So, bb represents 2 bytes. When passed function, it will parse out the first 2 bytes of data in the command string. These bytes, as you may remember, are the bytes for the load command and the data length. You'll also notice that in line 9, we are declaring and setting the variable POS. In line 10, you can see the use of this variable in string.sub. If you look at line 10, you can see that we define another local variable named command data. Command data is the substring of hex value that starts at POS and ends at the end of the string. We'll add some additional code that tests the value that string.unpack stored in the command variable above. We can see that if the value equals 1, we know that it is a load command. Therefore, we'll use another string.unpack to get the load num and load level from the command data that string.sub stored above. You can also see that we created a function named createHexValue. This function will pack a string in hex format, which is simulating the syntax of a string that would be returned from our dimmer. This is the hex value parameter that will be passed to the test1 function. When we execute our code, we see the following. We can see the packed string, which was passed into the test1 function via the hex value parameter. Below the packed string, we can see the command data value, which is 3 bytes, or 01, 4B, and 50. Next, we get the individual values in decimal format. As you can see, parsing a hexadecimal data message is somewhat more complex than parsing an ASCII string. To further assist you with understanding how we've used these Lua functions to handle driver data, we recommend reviewing the supporting document 401 Module 7, Lua Parsing Examples. We've included several additional exercises to demonstrate other parsing examples. Up until this point, we've been looking at examples of data messages that are coming from a device and received by the Control4 system. It is important to understand that this is only half of the communication cycle a two-way driver needs to utilize. Our driver also needs to send data messages to the device. Let's take a look at several Lua functions that will help us accomplish that. The first useful string function we will discuss is concatenation, or concat. In Lua, 2 consecutive dots denotes the concatenation string operator. Concatenation is useful as it enables us to join 2 character strings together. For example, consider the following code example. When we execute this in our Lua environment, we get the following. Here we see the concatenation operator used in its simplest form. Now, let's apply this to our dimmer light load. We'll continue to use the load command and load number of 23 with a load level of 80. As in previous examples, we'll create variables to handle the elements of the data string we'll send to the dimmer. You can see the variables in each line of the code. We've created a variable for our load number, which is 23, one for our load level, which is 80, and a variable named message, which will add our command name, load. When we execute the code, we can see the resulting string. If we examine this line, we can see how each of the variables are concatenated to form a data string that our dimmer will understand. The first element is the command name, or load, in quotations. You'll notice a space immediately after the D in the command name. This assembles our data in a way that places a space between load and the next element. Next, we have an open paren and the first usage of the concatenation function, or ... This is followed by our load num value, which is again followed by a concatenate function, and a closed paren. Next, we have a space. This will separate the load num value and the load level value. Once again, we have an open paren and the use of the concatenation function, or ... This is followed by our final element, which is the load level value. When we execute the code, we can see the resulting string. We can now send this command from the Control4 system to the dimmer numbered 23 and change its light level to 80%. Another Lua function that is useful in assembling data elements into command strings is string.format. String.format returns a formatted version of variables it has passed. String.format has numerous arguments that can be used similarly to string.match. These arguments consist of regular text and directives, which control where and how each argument must be placed in the formatted string. A simple directive is the character %, plus a letter that tells how to format the argument. For example, S for a string. Here's an example using the same variables as our previous one. Let's look at this line to see how string.format is used. You can see that the elements passed to the string.format function are surrounded by parentheses. They consist of our command name or load followed by a space. This is followed by our Lua argument %s, which will format this part of our final data message as a string element. This is followed by a space and another %s argument. Following this, we include our variables for load ID and load level. This ends the function. When we execute the code, we can see the resulting string. We can now send this command from the Control4 system to the dimmer numbered 23 and change its light level to 80%. The last example we'll review in this training video involves using string.pack to build a command string which will consist of hexadecimal data. Essentially, the string.pack function packs binary data into a string. If we look at the first line of the code, we can see that our load command once again has a value of 0, 1. Line 2 is where we create our function that will use string.pack. We'll name the function testpack. Line 3 is where we'll implement the string.pack function. Let's look at each parameter and see how they are used. The first parameter consists of a group of data modifiers in quotation marks. The first element is a B, or 1 byte. This will be our load command value, or 0, 1. The next element is uppercase H, which is modified by the greater than symbol, otherwise known as big endian. The uppercase H represents an unsigned short value in Lua, and the big endian modifier dictates the order in which the bytes will be ordered in our string. The big endian symbol, followed by the uppercase H, represent the load value in our data string. The last element we see is another B for a single data byte. This byte of data will be our load level. When we execute the code, we can see that the first 0, 1 is our load command. This is followed by another 0, 1 and a 38. 0, 1, 38 is the hexadecimal equivalent of 312, which is the load number we defined in line 7. Similarly, the hex value of 50, which represents our load level, is equivalent to the decimal value of 80, or an 80% load level. We can now send this command from the Control4 system to the dimmer numbered 312 and change its light level to 80%. As you can see, parsing data from a device and assembling command strings using device data represents one of the more complex aspects of driver development. We encourage you to re-examine the contents of this video and use the examples provided in the supporting Lua data parsing examples document to better understand the fundamental concepts behind using Lua to parse data and create command strings. Understanding these concepts will be required before progressing to the T-Series videos, where we will use a structured driver template to create Control4 device drivers. For more information on configuring Lua and Notepad++, please refer to this video's supporting document.